heavy flavor hadrons and as a probe of the Quark-Gluon plasma.
So thank you, Bruno. So let's start thanking the organization for the invitation. I apologize for showing up just today, but I had some other duties. But I'm sure it was a very great conference from what I heard from colleagues. Well, what I'm going to present to you is actually, since I noticed from the agenda that was a very heterogeneous conference with actually more focus on hadronic spectroscopy, not so much in relativistic heavy ions. I will present to you some of the results of the work that we are developing in our group in the Physics Institute of University of São Paulo. But I will give you, I'll try at least to give you a very introductory view first of this field. So I apologize for the experts that are around. That will be boring for you, but I hope I can at least keep you entertained regarding this physics. So as I said there, I'll try to show some recent results on the heavy flavor measurements that we are doing in our group using the data from the ALICE experiment. So I'll start first trying to motivate you for this kind of study. Why is it interesting to study relativistic heavy ion collisions, and also show a bit the ALICE experiment. Then I will show you some new evidences for the interaction of heavy flavor probes, in this case charm and built quarks, with the medium formed in these collisions. And I'll show also some results of our reference systems. I'll tell you, in heavy ions, we always need a reference to extract information regarding this interaction of probes with the medium to extract the properties of the medium. And then I will show, I'll very superficially just qualitatively give you some idea of few perspectives that we can have in this kind of measurement. Okay, so from the experimental point of view, let's say, when you are colliding relativistic heavy ion collisions, basically you are trying to understand the dynamics of these collisions, right? You are trying to explain what's going on during these collisions. And in this process, of course, you access fundamental aspects of the QCD. So the idea is really you describe what is happening in the collision, and for that you need tools, you need the theory, you need the understanding of very basic physics. However, a relativistic heavy ion collision, as you can imagine, is a very complex, a very complicated thing, right? Here is a very old and traditional cartoon from the field where we show, do we have a pointer, Bruno? Here, maybe? This guy? Yeah. So in this cartoon, we see that we start with the collision. Then you have some pre-equilibrium phase. Then you form something. You form a medium that we call that is exactly what we want to study, what we want to understand, how it is, what are their properties. Then you have a hadron phase, but a very interactive, a phase where these hadrons are interacting very much among them. And then finally, these guys keep expanding and interacting. And then what you really get in your detector is the very last phase, what we call freeze-out, when these hadrons, these particles, do not interact anymore. So our job in this field is, once we measure this thing, this very last stage of the evolution of the collision, to understand what happened in the beginning, what were the properties of this medium formed here. Is it our expected Quark-Gluon plasma? What are the properties of this Quark-Gluon plasma, and so on? So it's a really a very let's say, is a detective work where you try to infer from this final state what happened in the beginning. And, of course, the QCD, the theory, gives you a lot of predictions about that. And the main one is the formation of the plasma, of the Quark-Gluon plasma, that we have now overcome any doubt that it's formed or not in laboratory. We have a lot of evidences about it. But so we want to, in the beginning, just to see if what we have in this phase is a bunch of hadrons or really this plasma. As I said, now we are pretty much convinced that this is the case. So, but now, once we have convinced ourselves that the formation of this state is there, we need to understand the properties of this plasma, understand how it really behaves in order to really understand the fundamental QCD that's behind this state, right? And of course, there's also this kind of propaganda that this QGP is important for also a more cosmological view or studies because of the primordial matter of the universe, okay? So now we are trying to understand how is it possible that it is formed and what are the properties of this guy. Well, in order to do experimental studies on this, there are not so many places in the world to do it. So basically we have, if I'm not mistaken, 4 accelerators doing relativistic heavy ion collisions. So we have in GSI, this is 18. SPS at CERN, who is now the injector, is the accelerator that's in the injector of the LHC, is still doing, studying relativistic heavy ion collisions. The RIC, relativistic heavy ion collider in Brookhaven, very active with the STAR experiment now. And also, of course, the LHC at CERN. So I will concentrate in the last one, in the LHC, since I will talk about the results from the ALICE experiment. As you all know, most probably, this is the accelerator that generates the highest energies in the world. So we have there proton-proton collision, different values of center of mass energy. Also, proton-lead collisions that we'll talk about. Last year, we had some xeon-xeon collisions, and also we have been lead-lead collisions in these 2 energies. So this is our main, of course, topic. This is what we are most interested in studying. So the ALICE experiment is a large experiment, as everything in this field. Here, to give you an idea, the people here in comparison. So there are many systems that compose this detector, like the time projection chamber. There is an inner tracker, time of flight, electromagnetic calorimeter, and so on. So several systems that allow us to reconstruct the track or the trajectory of the particles formed in these collisions, measure their momentum, measure their vertex to see if it's a primary, a secondary particle, and also identification of particles to see ions, protons, and so on, using the energy laws in the TPC, in the ITS, or the time of flight system, right? Okay, so experimentally, how we can try to access from this last stage what's happening in the beginning. So basically, I like to divide this search or these studies in 2 parts. So one is try to see if there is any manifestation of the formation and the properties of this plasma in the late stages of the collision. So is there anything, any property, any behavior that are characteristic of these very first stages of the collision that survive all these interactions, and you can still see it in the end? And another kind of observable is what we call high energy or hard probes that allow us to do a kind of tomography of this
medium. And the idea is something very Rutherford-like, where you have a probe that is, you know that was produced in the very beginning of the collision, and that this probe survives the time life of this plasma, of this medium, and come up in the end in your data. So you have a probe that is really like a tomography that you throw in your medium, it comes out, and you see what happened during this interaction. And of course, to do that, to do any of this, actually, you always need some reference. You always need to compare the results of what you measure in lead-lead collisions to the same thing or similar thing that you measure in proton-proton or proton-lead collision. Like you need to compare the results of these two kinds of collisions to make sure to extract what is different, and so what really happened to these probes, to these observables, due to the presence of this medium, right? So now I'll show you a few of these observables that's going to appear in my results, and I'll try to explain these observables because if you are not used to them, it's not so trivial to understand. So one of them is this so-called anisotropic flow that is observable that is really show up in the beginning of the RIC program. And the idea is, in a very simple way of putting it, when you are colliding two nuclei that are large, have a big volume compared to protons and neutrons and hadrons, you have an overlap region between these two nuclei. And this overlap region is not spherical. This is, you expect it to have this ellipsoidal shape, to have like a larger X and a smaller X. And why is it interesting? Well, the idea is if you have this elliptical shape, and if the particles or if the medium that is formed here is very interactive, the particles there interact a lot among them, the result of the expansion or the evolution of this medium, this shape will reflect on the momentum distribution of these particles in the azimuthal direction, right? So if the particles here do not talk to each other, then the shape doesn't matter. On the other hand, if they really interact, then you can see from the picture, it's much easier for the particle to come up in this direction than in this direction. So if we measure in the end the distribution of particles in the azimuthal angle relative to the direction plane, this shape will manifest itself in the final result. So here is just a simulation where you exactly start with this almond shape and you end up with this, right? And then in terms of quantitative terms, essentially what you do, you have this distribution in the phi direction, and then you can just try to fit a Fourier transformation to your distribution. And so for this almond shape, what you expected that the second order or the cosine of 2 phi will have an amplitude that's different from 0, right? So what you expect from this thing is that you have a peak here, a valley here, peak here, and a valley here. So then you have, if you look at this distribution, you see this modulation, right? And the amplitude of this modulation with cosine of 2 phi will give you this effect. So it's a way of measuring if indeed this shape, this thing that you formed in the beginning really propagate to the end. Right? Another and simpler way to look at these effects is what we call nuclear modification factor. That simply
the ratio between the number or the distribution of particles that you measure as a function of transverse momentum in nuclei-nuclear collision divided by the same quantity but measured in proton-proton collision. And of course, you need to normalize here for the number of binary collisions that you expect to happen in these lead-lead or nuclei-nuclei collisions. So if we, so from this ratio, if this ratio is 1, right? If you when you divide these two guys, you get 1. You get 1. It means that nothing really interesting happened. That nuclei collision is basically a bunch of proton-proton collisions, and nothing quite interesting happened. And of course, we can, and if you get a number that's different from 1, then, okay, something happened. And we can do that as a function of centrality, because again, since these nuclei are big, you have different collisions, you have different centralities. So you can select experimentally which collisions are more central. It means the impact parameter are smaller, so really head-on collisions. The ones that are more peripheral, and see how this ratio changes as a function of this centrality. So this plot is an old one. I'm just showing you to illustrate and to show you that what I'm going to show next is not new, but is more specific and precise. So here is shown this ratio as a function of PT. This is the ratio for different centralities. So here is more peripheral, here is more central, right? And then we see that for more peripheral collision, indeed, this ratio is very close to 1. And as you go to more central collisions, it gets much, much smaller. So this is an evidence that indeed something interesting is happening there. We don't have in nuclei, here in this case it's lead-lead collisions. It's not just a bunch of proton-proton collisions, but something much interesting, right? Okay, so these two observables are used. Now, let me talk you why heavy flavor is interesting for these studies. So the idea is that these charm and bottom quarks, as you for sure knows better than me, these guys are produced in the very beginning of the collision, right? Because they need this, the amount of energy that you have in the beginning of the collision to be produced. So they have a very short time, production time. That means that they can really probe or potentially probe this medium, right? We can even try to see if they thermalize with this medium or not, or basically how they interact with this medium. Oops. And I think what is most interesting is we can measure the energy loss of these particles in this plasma, in this medium. So if we just measure the momentum distribution of these quarks and compare to more basic collisions like proton-proton, we can try to estimate what is the medium density and size that's formed this collision. There are many ways to measure these quarks. In this talk, or what we are more focused in our group, is to measure charm and boson through the electron channel. So there is a fragmentation. They form mesons B and D, and these guys have a branching ratio to decay to electrons. And so we measure the electrons, and from the electrons, of course, there are a lot of experimental procedures to make sure that these electrons are coming from heavy quarks, but then we make sure of that, and we can so estimate what's happening to these guys, right? Another observable that is interesting in this sense is the Quarkonia. And in this case, this was proposed many, many years ago, that the formation of the Quarkonia in this medium would be suppressed due to some screening color screening in the medium. So if you have like the CC bar pair, because of a lot of color charge in this medium, you would suppress the formation of this quarkonia because of that, right? And they even, this mostly SATS and company, they even propose that if you look at different states of the quarkonia that has different sizes, you would be able to even probe the temperature of this medium. So depending on which of these states would be suppressed and which ones are not suppressed, you could maybe even infer this kind of information. But as life is not simple, in the last years, people realized that you could not only have suppress of the quarkonia production in this medium, but also enhancement just because you have more quarks available there. So you have a more dense phase space, so you could even form these particles because of great availability, let's say, of charm and bottom quarks there. So then you have a competition, basically, between these two mechanisms, but the study of the formation of these particles can bring us some information in this regard. And the last observable that I want to mention are the jets. So we know that when we collide like two protons, you can have a hard scattering of partons and produce the jet of particles, right? So you have a scattering of two partons that will suffer fragmentation, produce a lot of hadrons. So you basically measure the spray or the jet of particles back to back in these collisions. Of course, this is very nice in proton-proton, but when you go to heavy ions, then life is much more difficult. Then you need to find a way of finding these particles or these structures, these jets in the collision. And this is very interesting because, of course, if you have this parton propagating in a different medium, it's most expected that they will suffer some kind of effect, right? And then, so if we study the probability of formation of these jets, the structure of these jets, we can infer something about this medium, right? So it's a very interesting probe for the measurement of energy loss, a very good strategy, okay? So now I'll show you some of the results of some recent results from these probes, from these observables. And most of them, not, of course, as any large experiment, we don't do everything. Every work has the hands of different people, different groups, different universities, but the results I'm going to show you are mostly are the ones that we are very heavily involved. So here's the first result that I'd like to show. So it's basically this nuclear modification factor that I mentioned to you. So the ratio between the PT distribution of particles in lead-lead collision divided by proton-proton, normalized by the number of binary collisions that you expect to see in the lead-lead collisions, right? And the difference here that I'm showing to you is this RAA, this nuclear modification factor, but from electrons that come from heavy flavor. The previous plot that I showed was just hadrons, a general result. And here is for electrons from heavy flavor. So you see here, so the RAA as a function of PT, two curves. The black one, the blue one is for 276 TeV, and the black one, that's is the newer result, is for the higher energy. We see, similar to what we saw before, this is for 0-10% most central collisions. So we see clearly that for lower PT, this is compatible to 1, but then when you go to higher PT, a very clear suppression. So this is basically indicating to us that indeed these quarks are interacting with the medium. It's not something that is transparent to the medium. So great, we can really use these guys to study our medium, right? And just a remark, this is similar. So 5 and 2 is a small difference in energy, so the results are very compatible, right? Here, I show to you the same observable, but now what we did is to separate from the electron sample that we had those that come from the decay of beauty hadrons, right? So then we use a technique of, given that these beauty hadrons, they have a longer lifetime, they have a longer decay length, we can experimentally separate the electrons that come from the charm, or the electrons that come from the beauty from the inclusive sample. And so this is what I show to you in red, right? So the black is just, again, the RAA, the nuclear modification factor, given by all the electrons, given by B and C decaying, and the red one is the result for the beauty, the electrons that come from the beauty hadron. So what we see here is a difference, right? So it's although the systematic errors are large, we can see that is a clear trend of having a less suppression of beauty than charm hadrons. And this is also something that was expected from the energy loss point of view, because given the larger mass of these, the beauty quarks, we do expect that they lose less energy in this medium. So, and of course, so this is indication that we probably understand what's going on, but also the quantitative difference is very interesting for us to be able to quantify the properties of this medium, right?
Sorry, this is lead on lead.
This is lead, yeah. This is all lead till 10%.
If it was some other collision, would it change?
Well, we don't have, if you change the nuclear, you mean?
Yeah.
Yeah, no, we don't have, for this measurement, we don't have the results for the Xeon, but...
What would you expect it to change?
Well, yeah, if you have this different size of the medium, for sure you... Okay, this is another observable. That's basically, the idea is the following. When you measure the electron, you are measuring, let's say, the leading particle of the fragmentation process, right? You measure just, and even the electron, you bring just a part of the information of the momentum of that meson that decayed to this electron, right? So let's say you have a partial information of really the whole process. But, so if you measure the whole jet, and you the whole jet, or all the result of the fragmentation of that quark, you have a much better information, much better handle on what really happened to that parton during its propagation through the medium. So the idea is you measure a jet, you reconstruct experimentally a jet, and then you look for all, you go through all the jets, and you see which jets have some heavy meson in its constituents. So basically the idea is to tag your jet as a heavy flavor jet. So to see if that jet that you measured comes from a heavy flavor quark. And then the idea, once you have that, you can check if do the same thing as we did before, the nuclear modification factor, see if there is a suppression of jets. And even more interesting than that, you can study the structure of this jet. So like it got more wider, the distribution of momentum of the particles inside this jet has changed. And many things you can do once you have these guys, right? So that's the idea here. So one of the works in the group was to do this identification of jets that contains a meson D. So basically the quark C, the jet formed by the quark C, And of course, examine if there is any modification. Let's see my time, I have 15 minutes. Okay, so this is the result. So the basic result, or the first thing you can do, right? The nuclear modification factor of these guys. So what's shown in this plot, the RA is a function of PT. So the blue is just the nuclear modification factor for mesons D. So when you measure only the meson, you don't care about the jet. And in red is when you take the jet without any identification. And the black one are the points for exactly this analysis, right? When you get the nuclear modification factor of jets that contain a meson D. And we see that all of those guys fit on the same curve, so they have a similar behavior, let's say, that you, so the single particle and the full jet has the same, actually not the full, but the charged particle jet has the same behavior. Right? Now I'm going to the small systems because, as you saw, we are always comparing, when you do this observable, you are always comparing to proton-proton collision. So, of course, it's very important to know if we understand our reference, if we really understand what's going on in this more smaller system collisions. So here what I showed to you is, again, the electron coming from C and B. Here is just the cross-section as a function of PT. So the black dots are the experimental result, and the red curve is the calculation from Fronenel. And we see that, and this is for proton-proton collisions, 13 TeV, so the up and the highest energy in the LHC. And we see that for this case, and it's the same for other energies actually, we see that the points sit really on the top of the limit of this calculation. You see here is the ratio, so it's like really on the edge of the expectation, the theoretical expectation for the production of these quarks in proto-proto collision. So maybe there is room here to improvements. Another important test that we need to do is to check if the effects that we see in nuclei collision are really what we call final state effects, so an interaction of these particles with the medium, or for some reason, these, because of a different structure of the nuclei in the beginning, because of the high energy, has caused this difference in the final result. So basically, it's interesting to check if what the effect we see, like the suppression in the RA and so on, is really a final state effect, or effect of this medium, or something that happened because of initial conditions. And one possible way of testing that is to do proton-nuclei collision. So if you collide a proton with a nuclei, you try, and you see, if you see any difference, like in the nuclear modification factor, if that ratio is different from 1, so you know that there are other effects other than that are not caused by this medium that you form in these nuclear collisions, right? So here's the result for proton-lead collisions, 5 TeV. Again, electrons from bottom, beauty and charm as a function of PT. And you see that the result is pretty much compatible with 1. So at least in the heavy flavor sector, we do not see any effect that comes, what we call cold nuclear matter effect, that comes from the initial state. Just to show you some more results on this respect. So here I just show you the same ratio, but we call QP-LED, just because we made this measurement in different, let's say, multiplicity classes in this collision. So you can, when you have the proton-lead collision, you can divide this collision. Is not exactly centrality, but It's more like a multiplicity difference. And you see that when you get, let's say, more central events or more peripheral events, you still get the same behavior of a ratio close to 1. And we can also, to make sure, because of the reference, you can question this reference in PP, we can do what we call QCP. That is just the ratio between these most central to the less or more peripheral collisions. And again, so if you do 0, 20% divided by 60 to 100%, again, everybody compatible to 1. So it seems that it really, the effect that we see in lead-lead is not, at least in the heavy flavor factor, is not due, sector is not due to any initial condition. And the last observable that I like to show to you, I think is the last one, is what we call a correlation. So it's basically what you do, you build a distribution of, so you take like an electron from heavy quark, and you calculate the phi and the eta angle difference between these electrons from heavy flavor and all the other particles, or not all, but you select in PT, but all the other particles from your collision. And then you just look at the distribution of this delta phi or delta eta distribution. So here what I showed to you is for, again, proton-lead collision, the delta phi distribution for more central and more peripheral collision. The black more central, the red more peripheral. We see these two bumps that what we expect exactly from this jet structure in the collision. So if you expect a bunch of particles around your leading particle and a bunch of particles 180 degrees away from your leading particle, right? And the interesting thing here is the fact that when you go from more central to more peripheral, there is a difference in these two distributions. And we see that this, when you do the difference between this high multiplicity and low multiplicity, basically what you do, you subtract or you extract the structure due to this jet formation, and what you expect to remain in your distribution are exactly that anisotropic flow that I mentioned to you in the beginning. So the idea is, basically in this case, the idea is to measure, is there this effect of anisotropic flow in proton-lead collisions? Because in lead-lead collisions, we know there is this effect, is there. I didn't show it to you, but this is a very established, very well established. But in proton-lead, this is one way of checking that, and more than that, check if this, if the heavy quark is sensitive to this effect. And what we see from this result is really when you subtract this high, the low from the high multiplicity distributions, you get this modulation. You can fit that Fourier distribution. Then you get, in red here, are the points, are the amplitude of this V2 compared to the charged particles also in proton-lead collision. So the very interesting result here is the fact that we can see here that heavy quarks in proton-lead collisions suffer this effect of flow. Okay. And actually, there is just one last measurement. I'm going late already, but this is just so I mentioned to you Quarkonia, and also we have some work on this sector too. The JPSI, here is the JPSI measured in also, here is in proton-proton collisions. Basically what we do here, you count the number of JPSIs, divide by the mean value for all collisions, and you plot this as a function of the multiplicity of, or the multiplicity of the proton-proton collisions normalized to also the average value. So like number 3 here are events that you have 3 times more multiplicity, more particles produced than in average, right? Or than the mean bias. And what we see when you plot, so this J-psi as a function of this multiplicity in proton-proton, we see this, that there is this a kind of non-linear or faster than linear increase of the J-psi in these more higher multiplicity proton-proton events. So this is actually just one more evidence that in proton-proton collisions in the LHC, mainly these higher multiplicity collisions, they are really very interesting systems to be studied and to be understood, because it seems that they have some different behavior, right? Oh, and here just to show you that same measurement of jets tagged with D meson, but now not for lead-lead, but for proton-lead. And in this case, when you use some models, you seem to get a good description of these guys. So basically, what I try to show to you is the fact that heavy flavor is indeed a very nice probe of this medium formed in lead-lead collisions. We see a clear interaction of these guys with the medium. And now, here's just to illustrate to you. Of course, I cannot say much about all these models, but you see that a lot of models that try to reproduce these curves, both the RAA and the V2. So the fact that we see these heavy quarks interacting to the medium is not new, but there are a lot of new results that bring more precision and constraints to these models, right? And then we hope with these comparisons of the data with these models, we can extract these properties. So I'll jump, I'll have some perspectives, but maybe just mention very quickly that one idea that, one thing that we could do now is not use only the Ds, but also use the electrons to tag the jets, and even go through, separate the electrons that come from C and B, and maybe have jets from B measured in these collisions. Right? So I'll just go through this quickly and go to the summary. And just repeating, so several new results. I think the results on proton-lead indicate a good understanding of our baseline, although some open questions are still there. And I think there are many new ideas, very good perspectives for model comparisons and new observables to try to extract information about this medium. So thank you. That he doesn't remember.
Salt. Sure, I know. Yeah, which basically, if it would be possible to do, you would be able to directly measure and observe on the polyatomic move expectation value.
Okay. Yeah. So I mean a kind of event engineering where you select events that. Oops. Be careful. Yeah. Yeah, I think in principle, of course, you can take a look. I think just the problem is really because of the efficiency. First of all, well, I presume that you did some quantitative estimation of how often you would have more than one charm produced in the event, but then you need to.
More than one, it's like 100.
So. But then you need to combine that with the efficiency of the measurement, and see if you can really get a good sample of events with the identification. But in principle, there's nothing.
Okay, Tobias.
So how could this D work express solution in LS? time is decay point of the d mesons?
Oh, yeah, basically what you do, you reconstruct the track, and you extrapolate this trajectory to the primary vertex, and you measure the distance of closest approach. And
what's the resolution you can achieve with that? So how good can you determine this discrepancy between the primary vertex and the decay?
Yeah, well, that's in the microns. But actually what we do, you use templates from simulation of this DCA value from Charm and Bottom. And then you get the experimental, the inclusive measurement, and you just try to fit these two templates on the data, and then the amplitude of each distribution gives you the fraction of each. So it's more like a statistic thing than really pin out each trajectory from which particle comes.
Can you comment on the possibility of having different ions at the LHC? Like we've been talking about oxygen.
Yeah,
is this
yeah.
likely or?
Yeah, it's.
Argon and oxygen. Because they did xenon, right? So we were talking
Yeah, xenon. Yeah, it actually was, I think, 2 or 3 days only, but yeah, there is a long discussion. I'm not sure. Like LHCb is asking a lot for this because they have now, although they do fixed target, they are able now to do fixed target measurements because they have this gas injector in there. They actually was built for calibration of their detector now, but they can do even real collisions there. So there are some, like say, pressure to do that, but I'm not sure what to. There is nothing in the schedule saying that, but maybe if the community keeps pressing,
I saw, just a comment on that.
Yeah.
I saw some certain report that the cosmic ray community would like to have some oxygen or nitrogen, something like that in the beam.
Right.
So they would do proton, oxygen, or proton.
Yeah, to reproduce what happens in the atmosphere. Yeah.
Simulate what happens in the air.
Since I'm not discrete, I have a question for all of you. You mentioned it, right? This initial and final state competing effects. So, for instance, harmonic suppression. So there's this whole industry that works with effective Lagrangians to calculate the breaking out of JBSI. Is that experimental? I don't know if I got it. Is that an experimental way to separate what could be rather an initial effect or?
Yeah. The only thing that you can do is really to compare like a nuclei with a proton nuclei collision. Then you make measurements in forward, backward rapidity where these effects are more pronounced, right? And then, but from the experiment point of view, the only thing you can do is really measure proton nuclei collisions in very broad range of rapidity, so see how it changes.
Georgia?
Just as a comment, because it's relevant, in my humble opinion, which you can agree or disagree with, the humongous issue with LHC as a whole is that there is very little measurements away from the rapidity. And in particular, you were talking about PA as a comparison measurement, but PA is rapidity asymmetric, while AA is of course symmetric.
Yeah, sure.
Don't you think that this could really screw things up for this measurement?
Well, you have, for instance, LHCb that is a very forward, although it's not, but you can change also just the beam, but it's a very forward detector, right? Even in ALICE, there are some studies to build a forward calorimeter to measure also more forward than we have now. So, yeah, I think something that's missing, but I think there are some alternatives to fill up this gap. Yeah.
Okay, so I think we should move on to the next talk. Thanks, Marcelo, again.
Thank you.
We're now wrapping up this workshop from Mr. Jorge Noronha, who comes from across University of São Paulo.
Oh. Does this work? This guy?
Yeah. You can also,
For the
if you
slides?
want to switch the slides, there's a piece you can take out and put it in your
Oh, yeah, I would like that. Cadê? Bota aí.
This is USB, right?
Mhm.
Let's check whether it works.
It will work. Okay, so my name is Jorge Noronha. I'm very glad to be here. I thank the organizers the chance to come here, and I'm the only person preventing you from going to lunch and also going to Carnival, I guess. Today is, I guess, the first day of Carnival or something like that. So I changed my title like Georgia did. Georgia disappeared, okay. But actually I realized after changing my title to this, high density matter out of equilibrium from the lab to the sky, I realized that my talk is actually about this. It's relativistic fluid dynamics from the lab to the sky, okay? So we will see relativistic fluid dynamics appearing in different setups in experiments related to heavy ions, and now also in neutron star mergers, okay? That's the point of this talk. Okay, so first, let me remind you of why fluid dynamics appears everywhere in physics or in nature. It appears everywhere because it's based on very general things. So it's based on conservation laws, for example, of energy momentum or charge, and also the hypothesis of a large separation of length scales. And this happens in several different phenomena in nature. So when I say the separation of scales, what I'm saying is that there is a big scale that I call microscopic L, and also a small scale, the microscopic L here. And with this, you define a quantity, which is more like a field, that we call the Knudsen number. When this number, the little and the large here, when this ratio is much smaller than 1, you generally call this a fluid, okay? And this happens everywhere in nature. For example, here, this is a real simulation of the flow passing by a car. So the big scale is the scale associated with the motion of humans, like meters. And the small scale is associated, for example, with the mean free path of the particles, here the molecules and the gas, okay? This, to a very good approximation, this is a fluid, like the air in this room. Okay, so how do you describe fluid dynamics, at least in this simple non-relativistic limit? So we use several things: conservation of mass, whatever passes by a surface continues through another surface, Newton's second law, and some other things like isotropy and compressibility, for example, and you end up with a very famous equation. This is the Navier-Stokes equation. On one hand, here on this side, you have the idea of a perfect fluid, so the ideal fluid, there's no viscosity here. V is the variable, this is the velocity of the fluid in each point of time and space. And the interesting thing is that you have the ideal part that doesn't produce any entropy, and then there's this part here. This part will be the part that produces entropy, and this is where the viscosity comes in, okay? And in terms of that small number, that Knudsen number, this is of order 0 in the Knudsen number, and this is of order 1. So imagine that on this side here, you can do a Taylor expansion. And the difference is this, so this is like water, and this is a very viscous fluid like honey, so you see that there is a difference when you put in this term or not. And this coefficient is a famous coefficient called the shear viscosity, and it basically measures what happens when the flow goes in this direction, but it has a gradient in this direction here, and you measure the force that appears in the system. Great. So this is all non-relativistic fluids. So the Navier-Stokes equation, so this is, I guess, Navier, and this is Stokes. So this is valid when this separation of scales is very obvious, okay? So when the Knudsen number is very, very small. And it's an interesting equation, right? It's a type of equation that, you know, when you go to bed, you're like, okay, I think I can solve this analytically. I mean, it doesn't look that hard. You have just a vector field here. You have the gradient of pressure. You have a Laplacian. Normally, this quantity is like a constant. But it turns out that it's a notoriously hard problem to solve, okay, in 3 dimensions. In fact, there are several physical phenomena associated with this equation. For example, turbulence, like here. This is actually an actual drawing from Da Vinci 500 years ago, trying to describe the turbulence of some water going to a chamber. And in fact, there is a Millennium Prize problem at the Clay Institute, is that basically you have to prove, given a very good initial condition, a very smooth initial condition for these equations, you have to prove whether the solution exists or not at arbitrarily large times. So this looks easy, but it's not. Turns out that it's not easy. And in fact, if you can prove this, you get $1 million. But this is certainly the hardest way to get $1 million nowadays. Okay? Great. But the talk is not about simple fluid dynamics, but in fact, it's about the frontiers of fluid dynamics. So the frontiers of fluid dynamics happens when you redefine the big scale. So now your big scale is, for example, the size of a nucleus. Okay, so you redefine your macro scale such that now these big scales are relevant for nuclear particle physics. Okay, so that's what I'm saying here. So for example, imagine that your big scale now is the size of a nucleus or even a proton itself. Another frontier of fluid dynamics is whatever happens in the collision of neutron stars. Right? So there you have really the extremes. You have gravity, very strong gravitational effects. You have strong, in general, also electromagnetic effects. And now people are trying to understand this after the recent measurement in 2017 of the collision of neutron star mergers. So this is defined as also frontier of fluid dynamics. Both things you're going to see in this talk. Okay, so before I talk about fluids or things moving out of equilibrium, let me go back to the only thing that we actually know about QCD in equilibrium, which is this. So after many years, now we understand, or after several calculations on the lattice, we know what the pressure is. This is the pressure divided by 10 to the fourth. So imagine a QCD system in equilibrium without any chemical potential. And what you see is that the pressure transitions from a very small number here, associated with the physics of hadrons, towards a larger number associated with quarks and gluons. Okay? This, we know, it's okay. The rest, we don't. As this thing tries to go out of equilibrium, it's very, very hard to describe. In fact, the question about trying to understand the properties of non-equilibrium QCD go back a long time. So this is a photo of T.D. Lee, and it has a very, very interesting paper about something completely different. But the interesting thing about this paper is the very last phrase. So the very last phrase that he said is, in order to understand the properties of the QCD vacuum, here at zero temperature, this is a lattice simulation, we have to be different than particle physicists. Particle physicists like to put a lot of energy in a very small region of space-time, while here we have to do the opposite. We have to put a lot of energy in a larger region of space-time and see how this system and how the energy flows. Okay? And this is the origin of all these ideas that culminated with what we're seeing, for example, we just saw with Marcelo's talk for the heavy ion collisions at the LHC. Okay? Good. So this is a version of heavy ion collisions from a theorist. Marcelo already talked about the different phases, the beginning, the intermediate phase, the Quark-Gluon plasma phase, and this thing expands and eventually is detected here. The interesting thing for me is that heavy ion collisions is the ideal laboratory to understand how QCD behaves out of equilibrium. Okay? So that's the way I see it. And one of the things that, became clear over the years is that whatever this QGP is, this Quark-Gluon plasma, is certainly the hottest, the densest, the smallest. See, the size is not much larger than the size of a nucleus in general. And most perfect liquid. This part I'm going to talk to you about now. Oh, it's not showing up. That's not good. Let me see if I go back and forward. Yes. See, well-known bug in this open office. So the idea of nearly perfect fluidity, it's an emergent property of QCD. No human being, before this was discovered, knew that QCD in this limit would behave like a very, very good liquid. I think it's fair to say that. And basically the idea is, once you measure how these particles get to the detector, you measure the angular distribution. And for example, this is a coefficient that Marcelo talked about. This is the elliptic flow. This is the triangular flow. And this is for the Atlas experiment, for example. And one thing that it became clear over the last decade is that we can describe these yields, really the angular and the whole pattern of the collision very well using relativistic hydrodynamics, where the viscosity is very, very small. Okay? So the viscosity, so this is the shear viscosity divided by entropy density. It's a very small number of the order of 0.1. Just for you to have an idea, for water, this will be basically 2. Okay? So it's a much better fluid even than water. And this is just a simulation of what the temperature looks like as it evolves as a function of time. So this is the transverse plane. See the units, they're measured in Fermi. Okay, so as the system expands, this temperature drops because the system is getting colder. Good. Since Marcelo already talked a lot about heavy ions, and you already got the general idea of what's going on, I decided to divide the rest of the talk into basically 3 big questions in the field. 2 of them will be somewhat related to high density matter, which is relevant for fair physics, while the first one is a sort of a mystery that we're trying to understand now that happens at very, very large energies at the LHC. It started at the LHC and now it went back to RIC. So let me tell you about these big questions. So the first one, how does this liquid-like behavior really emerge in QCD? How does this appear in QCD? That's the first question. So first, let me tell you about relativistic fluid dynamics. So if you remember in that old Navier-Stokes equation, the main variable was the velocity field. Here, the main variable is the energy momentum tensor of the matter. So this is a conserved quantity. So the energy momentum tensor tells you about the energy density, the energy flux, the momentum density, everything you need to know about the distribution of the system. And the way you do it, the way you describe it is very similar to what was done before. You divide the whole system, in this case the energy momentum tensor, into 2 pieces. The first piece is the ideal part, the part that doesn't produce entropy, which is this guy here. See, there is a pressure here given by the energy density through the equation of state. And then there's the rest. The rest is the complicated part. This is the dissipative part. Okay? How would you determine this dissipative part? It's very hard to do that from first principles. So what is actually done, like any other physicist, you do a Taylor series. Okay, so this always works. So the standard view, in fact, for the past 100 years, is that you do what is called a gradient expansion. You imagine that the fluid is, for example, in local equilibrium, and you expand in gradients of the fundamental variables, which is, in this case, for example, the temperature and the flow velocity. Okay, you can put more and more corrections, and then, in principle, you think that the system is getting out and outer, getting farther and farther from equilibrium. Okay, so in this sense, hydrodynamics is truly seen as an effective theory in the modern sense.
Sorry.
Yes.
Why doesn't have temperature?
It does have temperature. It's, sorry. Oh, sorry. It's right here. It's within the energy density and the pressure via thermodynamics. So the temperature is inside this here. Yeah, because epsilon, for example, is like T to the 4th. Okay? Great. So, in fact, any transport coefficient, shear viscosity, for example, enters here. And as you go to higher orders, you get more and more and more coefficients. Okay, so now that you sort of understand what hydrodynamics is and why it's so general, let's try to see if it was crazy to try to describe this Quark-Gluon plasma formed in colliders as a fluid. Maybe it wasn't that crazy. So in fact, at first, basically before 2010, it seemed that hydrodynamics was, pretty justifiable, because this was what the energy density, what we thought the energy density looked like in calculations, okay? So it's a very smooth fluid. This is the energy density, and this is a transverse plane. So if you were to do that game with the big and the small scale, the big scale, it would be 1 over L, basically the size of the nucleus, okay? And while the micro scale is like 1 over the temperature, so, maybe like a Fermi, if you divide these numbers, you get something for the Knudsen number to be of 0.1. Okay, that sounds like a small number. If you do a Taylor series, it should work. And in fact, it should work if you had to do fluid dynamics at the scales relevant for the size of a large nucleus. However, yes? Sorry? L is the big scale. In this case here is the gradient of a conserved quantity like energy. Okay? Reality is much more complicated. Nowadays we know, after several different works, this is just one of them showing this type of thing, that the energy density is not a very smooth thing at all. And in fact, it has valleys and very big little mountains of energy here. There's structure all over the place. So there are very, very large spatial gradients at early times. So if you actually compute the Knudsen number, you see that it's large pretty much everywhere that it interests you. Okay? So that idea of a very controlled expansion should not really work. However, that's the idea. There's actually like a paradox here. This Knudsen number is not small, but hydro in the sense of hydrodynamics, comparing, doing your calculations and comparing to data, works very well. And in fact, works extremely well to the point that Marcelo showed those, mentioned those nuclei colliding like the xenon. Okay? So people made predictions to the level of like 2 or 3%, and it was confirmed. Okay? So whatever this is, it works very well, and we don't understand it. This is a fundamental question that must be resolved. And in fact, experimentalists did even worse. Instead of just consider very, very large nuclei, they consider smaller systems. For example, proton and gold. You see, this is a model for what the size looks like now. You see, instead of being 10 Fermi, now it's like 1 or 2. You reduce the big scale by a factor of 5. And for example, D gold and helium gold, and this is what you would expect from hydrodynamics. As you squeeze on one direction, that direction that gets squeezed expands. Okay? And this was studied in detail for these systems at RIC by the Phoenix collaboration. And lo and behold, again, predictions were made, and in fact, 4 years before the experiment, and they worked perfectly. So this is the anisotropic flow, V2, V3. So the data, like the data points here, and those are the calculations. Other people can do better calculations than that, I'm assuming, but the whole idea persists. Even if you reduce a lot the size of the system, this hydro thing still works. And in fact, this highlights the importance of this question that collective behavior now appears even at scales of the size of a proton itself. Okay? So the problem becomes much more interesting in this sense. And this is the big question for the young people in the audience that want to solve. How does fluid dynamics emerge from the well-known QCD interactions? I don't think anybody really knows how to do that. If you do, please let me know. Another big question. So the first one was related to physics at very, very high energies, very large collision energies. Okay? Yes?
So is it possible that you're actually using the wrong scale and then your Knudsen number is...
Yeah, so we don't know the viscosity. The Knudsen number depends on the viscosities, and in general, we don't know how to compute them. We have several approximations, several different models, but we don't really know how to compute them from first principles. And there is some leeway there. You can put a factor of 2 or 3, but still the problem would remain as you keep decreasing the system and you still see the same signals. Okay? I don't think it would go away. It's not a problem of, it's just a factor of 2. No, it's a more fundamental issue. Okay, the other big question, this is related to physics at finite baryon density, is this. This is my way to understand what happens as you start to squeeze the nucleus. How can one assess non-equilibrium effects in a system that has a critical point, right? So critical point, normally you understand that when you talk about phase diagrams, so system in equilibrium. So what happens now if you get this system and you consider it to be completely far from equilibrium? Does the critical phenomenon somehow affect the evolution of this system? How does it go back to hydrodynamics? Does it have a well-defined hydrodynamic behavior? So these are questions that we're trying to understand. So this is the QCD phase diagram. I'm sure that you've seen many of those diagrams this week. So this is a current cartoon showing the different phases. There's a phase at very high density called superconductivity. There is a hadronic phase here. This is the part that we understand from first principles in equilibrium. Very small net baryon chemical potential, very large temperatures. And there are several different structures that could be a first order phase transition. And then that will be the case. There's a critical point. We don't know the location of this critical point yet. But while it's interesting that the only thing that we truly understand is this part from first principles, it's safe to say that the whole rest of the phase diagram is not really known. And the reason why, it's a very deep reason, is the sign problem. that appears in these calculations. So if you try to do the same type of calculation that you did in equilibrium, but now try to put, for example, a chemical potential, you will see that the very fundamental techniques that you use to compute the properties of QCD on the lattice will not work. So you have to do something else. Okay? So this is the time to try different approaches, more analytical approaches, models, or different things, or maybe trying to solve the sign problem. That'll be a good thing to solve too. So there are several consequences of the sign problem in QCD. So first, the majority of the QCD phase diagram is unknown. The equation of state of complex stars, and in fact, the equation of state for the highly dense matter at FAIR is not really known. In fact, even the location or even the existence of a high temperature critical point, this guy here, it's still unknown, right? It would be nice if we could at least answer that. In order to understand these things experimentally, there are several programs. So first, there's going to be here now in 2019, the RHIC Beam Energy Scan 2, which is a large experimental effort to probe this baryon-rich part of the QGP, trying to go into this direction here, using heavy ion collisions at RHIC. And of course, the future is FAIR, and also NICA. And it'll be very nice when these things are really operational. So what happens when you try to understand hydrodynamics now that not only you have temperature, but you have chemical potential, right? So the first thing that you have to remember is that for these experiments, trying to understand the strong interactions, you don't have just one conserved current, like baryon number. You have at least three. For these experiments, baryon number, strangeness, and electric charge, they are conserved currents. So not only you have to consider your T mu nu and do all the dynamics that could be very complicated, but you also have to take into account the effect of these three conserved currents. Okay? So there are many new uncertainties in relativistic heavy ion modeling in this case. So in general, there are four different ways where viscosity can appear. So the first one is called bulk viscosity. It's basically, so this is this zeta here, this is the bulk viscosity. This guy measures the expansion of the system, and bulk viscosity basically tells you if you expand this thing radially, how much viscosity would affect this motion. Shear, on the other hand, is a more complicated beast. It comes with some indices. This guy is a Lorentz scalar. But shear basically tells you, I mean, this is in the name, how the flow is distorted via this shear effect. Diffusion, so these two were studied extensively in simulations in the LHC. But now, as you go to finite densities, diffusion becomes extremely important. So this is, basically the diffusion that you see here. You put some water and then some liquid, and you see how this thing diffuses. Now we have to do that with the QCD conserved charges, baryon, strangeness, and electric charge. And basically, there's a new transfer coefficient, which people surely, we don't even understand its magnitude. We don't even know what to expect for the size of this thing. We know that for the QGP at zero chemical potential, the shear viscosity is very small. This guy, we have no idea. Okay? And vorticity, this is something that I know that Giorgio likes very much. It's also related to polarization. It's a different way to include these effects. This is what the vortex lines would look like. And it's fair to say that this thing is also unknown, how that would affect the whole evolution of the system. Okay? Great, so there's a lot of stuff to do. And in fact, I would say when it comes to hydrodynamics at very low energies, the energies that will be probed in the RHIC energy scan and also at FAIR, not only the hydrodynamic part is that there are some uncertainties, but also the very initial conditions itself. So what happens to the nuclei? So what is the wave function of these nuclei when they come to collide? Okay, for example, in the case of RHIC. So we have to go back to the drawing board. Oops. In fact, there are a few items here that we have to talk about. So first, the simulations themselves became more complicated. We need the full three-dimensional dynamics in viscous hydrodynamics, and you have to include the effect of the conserved currents. This has never been done before. Okay, people have only included this current so far. We don't know the initial conditions. What happens to the nuclei in the beginning at very low energies? The effective theories that were derived that go with the name of color glass condensate, those are derived for very, very large energies. Okay? So this part is unknown. Also, from the hydro itself, if there is a critical point, how do you actually implement the effects of this critical mode on top of your hydrodynamically expanding medium? This is not known how to be done, how to really do in a realistic way. Also, transfer coefficients, how does, for example, the shear viscosity varies with the temperature and the chemical potential? We don't know. We have model calculations, but fundamentally, we don't know. And okay, this should be probably the first one. We have no idea what happens really with the QCD equation of state once you have these three conserved charges. We have very good understanding what happens when the charges are very, very small or the chemical potential is very small. There are well-known methods that you can do in lattice calculations to understand that limit. But as the importance of these guys grow, we don't know what happens to the equation of state. And in fact, there is also another problem that is very interesting. What happens to the hadronic phase at very large baryon density? Right? So in all this modeling of heavy ion collisions that Marcelo showed, for example, there is always a hadronic phase at the end. This is assumed to be a very dilute gas. Okay? It's not clear how the approximations made there and the very models that are used in these current calculations can be applied in this regime. So this, of course, but physicists, we are intrinsically bold. Even though there's a lot of stuff that we don't know, we do it anyways, right? And these guys did a very nice calculation. This is done by Shun Sheng and Bjorn Schenke last year. So what you see here, so Shun sent me this video. This is a central gold-gold collision at 19.6 GeV. Remember, the LHC was doing simulations at 5 TeV, so it is very low energy. And what you see here is, so basically what he did, if I understand it correctly, he plotted the distribution of temperature and chemical potential according to his simulation. And then you see how heavy ion collisions are probing the phase diagram. Okay? So it's, for those that remember, if there should be a first order line somewhere here, that's actually pretty interesting. Maybe this thing actually probes some of those interesting parts. His equation of state, though, did not have a critical point or a first order line, was just based on a Taylor expansion up to, for the specialist, mu to the 4th. So that makes a difference in how much this guy goes actually in T and mu B. Okay, so there are several challenges for the real discovery of the QCD critical phenomena in terms of heavy ion collisions. So the first is that the heavy ion system is not large enough, right? So it's not really an infinite system. So any critical correlation that it could have necessarily will have, finite correlation length. But this is actually not that bad. So people have studied this for a long time, not in systems that expand very quickly, but in equilibrium systems, but finite. So this is probably not the worst thing. This is actually a pretty damning thing. So the QGP phase only lives for a very short period of time. So it may not be long enough to develop these very nice correlations. And actually, since the QGP expands very fast, it's a very, very rapidly expanding medium, one has to worry about far from equilibrium effects. Can they distort or erase completely any critical behavior? So the idea roughly is this. If this is a QCD phase diagram, each point here, you consider a system in equilibrium, right? If this was a condensed matter plot, each point is a point in equilibrium. If you have imagine that you have another plot, another axis that tells you about the out of equilibrium effect, it could be that you're actually on top of the critical point, but the system is so far from equilibrium that you may not actually see the effects that you want. That's a possibility. So how do you deal with this? If you want to do calculations in QCD, very far from equilibrium, so imagine that you have a system completely out of equilibrium, how would you do this? There are several ways to try. The toy model that I normally try is called the IDSFT correspondence, and this is what I'm going to explain about it. It's just the spherical cow approximation of gauge theories. In fact, I would say there's a far from equilibrium spherical cow approximation for gauge theories, okay? So, but what we actually do at the end, we do this thing, we engineer solutions of black holes and see how these systems behave out of equilibrium. One of the things that we tried recently in this paper here was to understand, using this setup, how hydrodynamics appears if you have a system that has a critical point. This system is not QCD, okay, but it does have a critical point. It's a strongly interacting system that has gluons and some other particles. So even though it's not QCD, the question is actually interesting. because we can understand how new phenomena can appear far from equilibrium. We actually, the good thing about this setup is that this thing can actually be answered. So all the questions about this system is so simple, but it's so interesting that the questions could be answered. So this is for the specialist of Bjorken expanding system with a critical point. And there are several things that you see. So this is just how the pressure on isotropy, the difference between the transverse and the longitudinal pressure, vary with time. So this is a scale of time. So what you see here, you start completely far from equilibrium, and you see how the system goes back to something that looks like hydrodynamics. So that's what is here. So that's the idea of hydrodynamization. You start from far from equilibrium, really far from equilibrium, and these calculations tell you how the system goes back to something close to equilibrium. One thing that we saw is that, so there are several things into this plot, but the only thing you meant to understand here is that we can see is that if the system has a critical point, which is here, the onset of hydrodynamics is delayed. What it means is that if the system has a critical point, the time that it takes for the system to start from far from equilibrium all the way to something that looks like hydrodynamics could take a much longer time. That could affect simulations and some predictions for the dynamics of these phases. Okay? So these are things that you learn using these techniques. Okay, so the last big question, the last minute, is this. How does a lump of barren-rich matter behave under strong fields, for example, strong gravitational fields that you would see, for example, in a neutron star merger? So this is the idea. So we talked about the lab. Now we're going to the sky. This is a simulation by Luciano Rezzolla where he shows the collision of two neutron stars. So you see that the relevant scale is millisecond, as you can see here. So these things get together, they collide, they form something hot and dense, and this thing evolves and emits gravitational waves. So there is a fundamental problem in this field. And in fact, if you actually see all of these papers, every single paper you can possibly see that has to do with collisions of neutron stars, use, of course, general relativity and fluid dynamics, but it uses ideal fluid dynamics. There's no viscosity whatsoever in these calculations, whatsoever. And in fact, this goes back to a very big problem. It's an open problem in physics and mathematics since 1940 to try to understand how viscous fluid dynamics works within general relativity. There are several subtle issues there. And some people tried to study viscous effects in neutron star mergers. So it started in 2004, 2017, 18. But in fact, this was not real. There was no realistic simulation. And this, too, were also very early simulations at the time. So the very realistic state-of-the-art simulation that you see, they are for ideal fluids only. But then you could ask, okay, but maybe ideal fluids, it's a very good approximation. And in fact, the current assumption, in fact, since 1992, is that viscous effects don't really matter. And they don't matter because, you see, the fundamental scale that you need to do anything here is of the order millisecond. And based on the simulations and knowledge of the time, you see, 1992, it was estimated that the transport time scales, the things related to viscosity, they would happen in much different scales. So viscosity was not really important. And in fact, also, the temperatures at the time that they thought they could happen, they were not very large. The system was very smooth. So remember, this is like, almost 20 years ago in terms of simulations. And the gradients were very, very small. Remember, the viscosity goes with the gradients. If the gradients are small, it shouldn't matter. However, some people went back. So this is the paper by these guys here in 2018. And they studied in detail the different sources of viscosity in these simulations. So the first one is shear dissipation. After studying several different effects that could contribute to the mean free path of the particles there, they claim, so that's their claim, is that shear viscosity effects will be relevant only if you really have turbulent matter. And turbulent matter within general relativity, most likely it's probably one of the hardest things to do. Okay? So only if you have turbulence, this guy should be very relevant. Thermal transport is more relevant than shear, according to them, but also it really shows up still when you have turbulence. But there is another one. There's bulk viscosity. So bulk viscosity, according to their simulations, and there are several different arguments that justify this, bulk viscosity effects should affect these density oscillations that happen after the merger, and if so, they should affect the pattern of gravitational waves formed after the collision. That would be great, because not only from the gravitational waves you would learn about the equation of state, but you also would learn about viscous properties of this very, very dense matter. But there's a problem. This is one of the last things they say in the paper. The effects of bulk viscosity should be consistently included in future merger simulations. This has not been attempted before. It requires a formulation of relativistic hydrodynamics that is hyperbolic and stable. So hyperbolic here means causal, and stable means, if you try to put it in your computer, it's not going to blow up in your face. But of course, this is very complicated because it has to be done with general relativity. So the big challenge, which basically has been around since 1940, is to prove. So by being proven, like really mathematically proven, no one will try to put all these different equations in a code if you cannot really prove that things will be fine. Prove that the solutions of Einstein's equations, here, so this is the metric, the energy momentum conservation, so here, and also, in this case, just the conservation of baryon number. You have to prove that these things are well posed, or basically that the equations make sense. You have to prove that the solution exists and it's unique. It'll be very good if it's unique. And most importantly, you have to prove that the whole system of equations, Einstein plus fluid plus baryons, is causal. So it is okay with the principles of general relativity in the full nonlinear regime. Remember, gravity is very strong here. This is a hard problem. But of course, any physicist would say, let's go back to Landau-Lifshitz, right? So Landau, in fact, in 1950s, but Eckert before him, he already tried to understand what happens to Navier-Stokes in a relativistic regime. So basically, again, you have your ideal part and your viscous part. So this is the bulk viscosity. So these will be the equations that you will try to solve. Well, it would be nice if it worked, but it doesn't. This theory is acausal, okay? This theory does not respect causality, and it will be very, very hard for you to think about how to couple that to general relativity. And it's also unstable on top of that. And in fact, there's a very easy way to understand that. So even though the equations are nonlinear that come from here, at the end of the day, what they're like nonlinear diffusion equations, like this guy here, but with some nonlinearities. And if you remember, diffusion equation has a general solution of like a Gaussian, right? So this thing does not respect causality. In the non-relativistic limit, it doesn't matter. But in the relativistic limit coupled to GR, it does. So several people try to understand that since the 70s. The most important approach comes from Israel-Stewart. And basically their idea was this. You have to use your Einstein's equations, and also what we call the Israel-Stewart equations will be the equations for the energy momentum tensor, and also for how the bulk viscosity itself evolves as a function of time and space. So these are 16 coupled nonlinear PDEs, okay? You have to prove that there is causality in this nonlinear regime. As I said, this is an open problem in the field. And as you saw, nonlinearity in hydrodynamics is notoriously hard to handle. And in fact, if you talk to mathematicians, their idea would be, at least up to this point, is that Israel-Stewart equations, they are written in a weird way that in the nonlinear regime, it's really hard to put it in a box that fits into their well-known mathematical techniques. Okay, so mathematicians didn't know how to do this. But why is it hard? It's hard because of this. If you already studied quantum field theory, you care about light cones, right? So there's Paskin-Schroeder, page 53. You talk about causality and how things work. You have to make sure that whatever happens in this region, can only propagate within a certain cone, right? And you don't get regions all the way in the boondocks here that affect this point. But once you have general relativity, the cone itself is completely distorted because space-time is dynamical. How do you do that? How do you prove this? So what we did is that we did what every physicist would do. You ignore completely what mathematicians are saying. And you try to do it anyways. And that's what we did. We proved this now in January 2019. So basically what we did, we were able to see that this whole system of Einstein-Israel-Stewart equations involving the energy density, flow, viscosity, metric, etc., can actually be put into a form that is good enough to prove theorems, rigorous theorems with. So for those that would understand this, this is called the first-order symmetric hyperbolic theory. So this is a completely nonlinear regime. And in fact, with this, if you work a little bit, and you work with mathematicians, that's one of the co-authors here is a mathematician, we can actually prove, and in fact, this is the first proof of causality, existence, and uniqueness in the full nonlinear regime of viscous hydrodynamics, fully embedded with dynamical general relativity. If you want to be amused, try to read these theorems later. It's not written in a language for people, it's for mathematicians. Okay, conclusions. The unreasonable effectiveness of hydrodynamics, especially in very small systems, the size of a proton, requires extending our understanding of hydrodynamics towards the far from equilibrium regime. So there are new possibilities there, and there are many, many things that we try to understand that have direct experimental consequences. The emergence of hydrodynamics or hydrodynamic behavior can be significantly delayed by the existence of a critical point, at least according to those models that we can do using holography. It'll be nice to see that in other more realistic models. We were able to prove for the first time causality existence and uniqueness of Einstein's Rho-Stewart theory. And the importance of that is that not only you understand now a problem that was lying around for a few decades, but now we think that this paves the way for the inclusion of viscosity in these realistic simulations of gravitational wave signals coming from neutron star mergers. And now, maybe in the future, once these things are included, we'll know not only the equation of state of very dense matter, but also its transport properties. And I think that'll be cool. Okay.
Comments? Questions? Just a comment on top of the comment that
Sure.
you made in the middle. So you say that the Knudsen number shouldn't work to small systems because you're decreasing the large scale. But what
if the small scale goes together?
No, maybe the small scale is not the one that you're taking. It's something 10 times smaller.
Yeah, it could be, but it's very hard to think about something that would not be very similar to 1 over T, where T is the temperature. The temperature of these systems are hotter. PA is hotter than normal lead, but not that much hotter, okay? So I don't think it would compensate for that. And of course, there are other issues, right? If this is a well-defined series, you should try to put the first term and see if it's good. Then you put the second term and the third term. There are several technical issues that go with this. For example, this series now is known to not converge. So we have to find a way to sort of resum the whole thing. Very similar to what happens in quantum field theory when you try to do perturbative calculations. So I would say that it's not going to come like that, yes? It's an asymptotic series, yes, but now try to resum something where, the fields, the Knudsen number is not a number, it's really like a field. So it's complicated. We can do in certain models, but not in general. So I don't think, so you could say that maybe the small scale knows that when you go to a PA or a PP, it has to get smaller by the, correct amount. But, QCD is very nice, but I don't think it's that intelligent. I don't think it'll be like that. We have to be able to show that that's the case. So there are two situations, right? There are two solutions. One, hydrodynamics really doesn't require the system to be very close to equilibrium. Of course, if the system is in equilibrium or very close to it, hydrodynamics is known to work. But that's not necessary, okay? That's the first solution. That's the one I like. The second one is that everything that we measure in the end had really nothing to do with the fluid. It was just a very coarse, very broad experimental observable that any decent thing that would conserve energy momentum would give. I think that would be the bad solution. So Giorgio for sure likes the second one.
Well, no, actually.
So we could live without hydrodynamics.
Some people, at least for small systems, they try to understand that directly from QCD using this effective theory, this color glass condensate effective theory. And they do have some interesting things to show. So I think for large systems, it's different. For small systems, they have very interesting things to show. But on the other hand, the hydrodynamic behavior is very, very clear. So I don't know.
There is I think the follow-up was, no one knows what the Knudsen number is. However, we can make order of magnitude estimates about what system should have a bigger or a smaller Knudsen number. So there's a constant level of that. You guys, the experimentalists, have gotten good at LHC energies to compare events of TP, PA, NAS
It's harder.
Average Coulson number. It's true that the
Yeah.
Coulson number is a field. I'm averaging over there, but so I think that there is some weird things. Yeah.
So now that we know that there is a solution to this problem, can we get answer in a, for a simple problem in a finite time, or is this case that?
Yeah, so I'm not the person who would do these computational things. So the good thing that you know now that there is a solution is that, so the moment that we showed this, we talked to the specialists that solved these things numerically, and they were excited. They are starting to implement this. And since the interest in neutron star emergence is basically infinite, I'm assuming that they'll try to do this as quickly as possible to try to get a number on this bulk viscosity. Because we have an idea what it should look like at zero density and finite temperature from extractions from QGP stuff. And it would be nice to see what this looks like. But of course, I just have to say that the physics that is involved in this bulk viscosity is not the same microscopic physics related to the QCD one. So this has more to do with weak interactions. Okay? But it's a number that nobody knows. Well, I sent, no, in fact, okay, so the theorems are written in a full mathematical language, but the paper is written for people, so people can read it. It's actually not that long, it's just like 10 pages. Most of the important details are in the appendix, so you can survive by reading it. But yeah, it's, we just put on the archive. I hope that it's published soon.
Suggest in a long week. We should first thank George again.
Okay.
And with this, we close the workshop, and I'd like to thank all German, Swedish visitors.